previous section that the derivative, which is sometimes referred to as a first derivative, is also a function. Thus, it follows that we can also obtain its derivative, which we call derivative of the derivative or simply the second derivative. Now, the second derivative being a function gives us an opportunity to also get its derivative, which is called the third derivative. And the process can be continued successively up to the point that the problem requires. However, note that usually only the second derivative will be required as it has some of the commonly ascribed properties of functions, such as it can be interpreted as instantaneous acceleration of an object with a defined equation of motion. Furthermore, the second derivative provides an alternative way of knowing when an optional value occurs. Another competency you may need to have at the end of this section is to determine a general formula for the higher order derivatives. In this section, it is of prime importance that your pattern recognition and generalization skills are enhanced. This can be a great help for those gearing up to study higher mathematical analysis concepts related to sequences and infinite series. At this point, you had already been exposed to various rules of differentiation. With this, you can already continue getting derivatives up to particularly targeted result. Bear in mind that since the derivative is also a function, you can always get its derivative by a usual process of differentiation. Before proceeding, it is a must that you have learned familiar with the notations that we'll use in this section. In the earlier sections, you have seen the following notation for the derivative of a function defined by the equation y equals fx. First, the Leibniz notation dx. 2. The functional notation fx. Third, the differential notation dy over dx. And fourth, the prime notation f prime or y prime. As you read other advanced mathematical references, you will encounter other ways of denoting the derivative. However, for the sake of brevity, we shall dwell only in using for aforementioned notation. Furthermore, you should be aware at this point that the Leibniz and differential notation make use of operators dx and dy over dx. In principle, those operations can be attached on both sides of an equation, signifying that we have to take the derivative of each side in the given equation.
So our problem here is hx equals x squared cosine x. Our first derivative here is hx equals 2x times cosine x plus x squared times the derivative of the second part, which is the negative sine x. So we have 2x cosine x minus x squared sine x. So our h double prime x is equal to the derivative of the first part of the derivative of 2x is 2, and the second part, which we will leave cosine x, plus 2x negative sine x. The derivative of x2 will be the 2x sine x plus the first part x squared times the second derivative of the second part, which is cosine x. And now we will rewrite everything. So this will be 2 cosine x minus 2x sine x minus 2x sine x minus x squared cosine x. So we will combine the 2x see sine x. So this will be our final is equals to 2 cosine x minus 4x sine x minus x squared cosine x. So this will be the final.
We have here an example of fx equals 3x to the power of 5 plus 2x cubed minus 6x plus 4. And we have to determine the second derivative function. So we have to find the first derivative. So derivative of x to the power of 5 is 5x4. And derivative of x cubed is 3x squared. And derivative of x is 1. And derivative of constant is 0. So this is 15x to the 4th, 2x, 2 times 3 is 6, and so this is the first derivative. Now the second derivative. If we differentiate x to the 4th, that's gonna be 4x cubed. And the derivative x squared is 2x. So the second derivative is 15 times 4 is 60 x cubed plus, and 6 times 2 is 12. So it's gonna be 60x cubed plus 12x.
Good day everyone, so I'm Bianca. I'm going to discuss the next two examples for getting higher order derivatives. So we have the first, let me just write the example. We have 5x minus 9x cubed times 8 plus x squared. So for this equation, we're going to get we'll try, step by step solving for the second derivative. Let's try and get the second derivative. So of course, before we get to the second derivative, we're going to solve for the first derivative. So since this one is under the product rule of differentiation formulas, let me just write what it's supposed to look like. If you can remember, there's h of x is equals to f of x times g of x. And in getting the derivative of this one, it looks like this, right? So we have h prime of x equals the quantity of x, f of x, times g prime of x plus the quantity of g of x times f prime of x. That's right, it's like that. So we're going to achieve in getting this one in order to get the first derivative of this one. So first we are gonna have let f of x be equals to negative 9x cubed plus 5x. G of x is equals to x squared plus 8. Now I wrote it in this form. Wait, let me just, okay. So I wrote it in this form because this is the standard form wherein the variables with higher exponential value goes first, right? Because that's the standard form and it's easier for me. It's more, and for just the sake of consistency, we're going to stick to that. But if you're going to write it the way it is, it will just arrive the same answer. So for this video, we're going to do just that. Then second, the next thing we're gonna do is getting the derivative of each term. So we have f prime of x is equal to, we're going to times negative 9 times 3 is negative 27x, then 3 minus 1 is 2 plus 5, since x is equals to 1 in here. G prime of x is equals to 2x, since 8 becomes 0, and 2, we have a hidden 1 here. 2 times 1, 2. 2 minus 1 is 1, so this is also hidden one. Okay, and then we're going to do just this, right? We're going to do just that. So let me just write it here. We have h prime of x is equal to negative 9x cubed plus 5x times 2x plus the quantity of x squared plus 8 times negative 27x squared plus 5. Okay, that's that, right? Then we're going to perform the operations. Now for this one, just distribute. This one can be the FOIL method, right? Since it's just the same as a binomial. Then we get the answers. Negative 18x to the fourth plus 10x squared minus 27x to the fourth power minus 211x squared plus 40. And our final answer, since we can simplify this. There are, let's say, see, there's a base of x to the fourth power and x squared. Going to add those. We have negative 45 x to the fourth minus 201 x squared plus 40. This is our first derivative. Now in getting the second derivative, we are just going to times negative 45 times 4. Let me get my calculator here. Negative 45 times 4. That is negative 180, right? So we have negative 180 x cubed. Now this one, getting the derivative of this, negative 201 times 2. 201. We have negative 402x. This becomes 0, right? So this now becomes h. The symbol for the second derivative, or this derivative of the derivative, is equals to negative 180x cubed minus 402x. Now for our next example, we have the next example will look like this. Let me just write it. 2 cotangent x minus 7 cosecant x. Okay. Now, since this falls under the trigonometric differentiation formula, right, or theorem, so you should be able to know what the derivative for each trigonometric function is, right? So since we can divide this into 2, it would basically just look like this. We're going to distribute this one, right, for the first. So this would look for the first, let's just say this is the whole formula is a of x, right? And getting the, so let's just put let a, okay, because this is whatever works for you. For me, this is how, so that I won't get confused. 2 cotangent x minus 7 cosecant x. So the a prime of x is equal, so we're just gonna do that one, right? 2 cotangent x minus, like that, since there are 2 terms in this case, right? Then we can get the constant of age out, like outside, so that would become 2. Then cotangent x, the derivative of cotangent x is negative cosecant squared x, and then the derivative of cosecant x is this one. It's kind of long, so we're just gonna write it like this: negative cosecant x cotangent x, right? Yeah. Let me just recheck. Cotangent x, negative cosecant square x, and then cosecant x. We have negative cosecant x cotangent x, and then we're going to simplify our answer. So the final answer will look like this: cosecant squared x. We have negative and negative, that becomes positive. 7 cosecant x cotangent x. Now this one, that would be our first derivative. So for this case, let's try and get the second derivative as well. So this one, the second derivative for this we're just going to do the same procedure. We're going to distribute it, right? Negative 2 cosecant squared x plus d, okay, the derivative rather, sorry, cosecant x. So our answer for this one is 4 cosecant squared x cotangent x minus 7 cotangent squared x cosecant x minus 7 cosecant cubed x. This is our second derivative. So that's it for today's video. If you enjoyed it, please leave a like, comment, share, and don't forget to subscribe. Thank you so much. Stay safe and God bless. This is us from Group 12. Bye.